So acids and bases, who's ever talked about acids and bases in your life before? Excellent, so you already know some of this. So acids tend to dissolve things. Does that show up? That doesn't show up very well. I'm gonna switch my black pen. Traditionally, acids are associated with a sour taste. Think citrus fruits here. Lemon, lime, orange. So citrus fruits. How about pH, high or low? Low. Low pH. And when you're dealing with litmus paper, acids turn blue litmus paper red. Or if you use red litmus paper, it stays red. So on litmus paper, red equals acid. If you're going to be going on to organic, the organic acid functional group is going to be some, R doesn't matter, okay? R is just another branch of the molecule. What you look at is a carbon, double bonded to an oxygen, single bonded to a hydroxide group in any form. If you're going to be taking organic, you want to save this note packet. I'll point out some of the reasons why. We're not going to be dealing a great deal with organic acids, but if you're looking at a formula, you may also see it as COOH. So if you see Cu is going to be an acid in organic. Bases. Bases tend to feel somewhat slippery. If you think about a lot of hand soap, yes, they have surfactants, but they tend to be a little bit more on the basic side. They feel slick. Bases are traditionally bad and toxic to the body, so as a protective mechanism, we seem to think that most bases taste bitter. Bases are not all bad for the body. For example, if you're talking about dark chocolate, has a bit of a bitter taste, as does coffee. And it may depend on your own individual taste preferences as well. But to keep us from eating things like hemlock, they taste terrible. All right. Bases have high pHs. When we're talking about litmus paper, if you start with red, they turn it blue. If you start with blue, it stays blue. Not all, but generally the first time you learn about acids and bases, you will talk about the OH hydroxide group. Now somebody here is going to want to raise your hand and say, well, how is this an acid then? This is still an acid. It's going to lose this hydrogen. But, so they're going to have the OH, the hydroxide group. You do not have to have a hydroxide group to still be a base. We'll talk about that. But bases traditionally used in cleaning. So soaps and caustic cleaners like Drano. Very strong bases. Now this is not, what's that?
I thought Drano had an I in it.
It might. I think it's actually a long A, like that, but it doesn't really matter. Cleaning substances. But, so in basic organic chemistry, it's not, the bases are not carbon necessarily. It's organic, so it has carbon in it, but what makes most organic compounds basic is they have a nitrogen with a lone pair, and then they can have however many other R groups that don't have to be the same. But generally, if you're looking at at a formula or a structure of a compound, look for a hydroxide group or look for a nitrogen. That's going to be a pretty key clue that it's a base. Now, what makes an acid and what makes a base? It depends on who you ask. I think I broke this up in a little bit different order than the book might have, but anyway, it made the most sense to me. So the simplest definition of acids and bases are the Arrhenius definitions. These are the ones that you learn about first thing. Acids is any substance that produces hydrogen ions when it's dissolved in water. Now, most of the time, so aqueous, dissolved in water. So when you take hydrochloric acid and you mix it with water, generally we write this as the simple decomposition H plus Cl minus, which is not wrong. But specifically, what happens is this hydrogen that comes off from dissociating latches onto water. So a hydrogen ion plus water makes H3O plus. This is known as the hydronium ion. Depending on how specific a text or class wants you to be, they may prefer you write that. Most of the time we're just going to shorten it to H plus just because it's easier. But it actually means, H plus means this. It's just a shorthand way when you're talking about aqueous solutions. Bases produce hydroxide ions in aqueous solution. And these are just decomposition reactions. There's nothing that interferes with water. So you put a base, look for OH minus. So find H plus or H3O plus, that's an acid. OH minus, that's a base. We talked about this way, way long ago last semester in chapter 4, and none of you probably remember it. What happens when you mix an acid and a base? What do you get? Water and salt. Yes, anytime you mix an acid and a base, you get a salt and you get water. And we're not talking necessarily just table salt. We're talking about salt as in a metal and a non-metal combination. However, if you want table salt, hydrochloric acid, NaOH, run this reaction as a double replacement. So you get hydrogen matched with hydroxide and NaCl. If you can write water as H2O if you want to, that's fine. This is how I write them for double replacements because it makes it a lot easier to balance. And I can see that water is formed from that process. Any questions? Arrhenius acids. These are easy. Arrhenius acids and bases are very easy. Let's make it a little more complicated. Bronsted-Lowery, this is two people, worked together, and they decided, well, we can expand the definition of what is an acid. So they said This is the most common definition that we use, at least in Gen Chem. Acids are, by Bronsted-Lowery definition, proton donors. So here in this reaction, you end up with the positive ion. This hydrogen gets donated to water. If I'm actually drawing the mechanism correctly for people that care about mechanisms, it goes there. Don't tell Dr. Broadbent. So acids are proton donors, so bases would be proton receivers or acceptors. So acceptors is the definition, receivers works okay. If you want the football definition, passers, receivers, works okay. So using the Bronsted-Lowery definition, that's how we get the nitrogen-based compounds classified as bases. Because if you put ammonia, if you put pH paper or litmus paper in it, it's going to be a pH 9 around there. So how does that fit? Because ammonia does not have an OH group on it. So what happens here is you look for this lone pair of electrons. They are going to accept one of the protons from water to make an H4 and an OH minus. There's where you get the base. There's where the hydroxide comes in and where you see it. This is not as straightforward, so it's going to take you a little bit of time to practice finding what's the donor, what's the acceptor, and what it looks like. So you may prefer to write your chemical formulas in a different way. I find it very helpful to write water as HOH. It makes it easier for me. Now, this does not happen with Arrhenius solutions so much, but with Bronsted-Lowery definitions, a substance can be an acid or a base. What do we call that? Anybody know? All right, it is amphoteric. You may have heard that word before, but you didn't realize what it meant. So an acid or a base, the same compound can sometimes act as an acid, sometimes act as a base. It is called amphoteric. For the purposes of general chemistry, there's only two of them that we're going to talk about. We're going to talk about water, and we're going to talk about ammonia. And you're going to go, but you just told me ammonia is a base. Yes, I did. Ammonia is traditionally a base, but it can act as an acid. So I'm going to show you. If you mix something that is acidic with water, you get H3O+. In that case, is water, think Bronsted-Lowery, is water donating or accepting a proton? It's accepting. So a proton acceptor, Bronsted-Lowery says, is a base. So water is acting as a base in this situation. All right, again, if it helps you to rewrite water as HOH, please do so. The book does not do that, but I do. We all know I'm not a very good spatial thinker. So, all right, if you mix a base with water, you get hydroxide. So in this case, is water donating or accepting a proton? It's donating a proton. So when you donate protons, is it an acid or a base? It's an acid. And You're gonna go, but water is neutral, right? That's why we're saying water is acting as. Water is acting as. Just like ammonia is traditionally a base. However, if you mix an acid with ammonia, does ammonia accept or donate the proton? It accepts it. So that means it is a proton acceptors. Bases, yes. I know there's a lot of mental gymnastics here. If you take a base, something strongly basic, and you mix it with ammonia, it becomes NH2 minus. So is ammonia donating or receiving the proton? It's donating. When it donates the proton, it acts as an acid. It's going to take some time and practice to wrap your brains around that. I understand that. It is okay. Who thinks it sounds backwards? Nobody's going to admit it? I thought it sounded backwards for a long time. Now, mental gymnastics here. If it is an Arrhenius acid or a base, it is going to be a Bronsted-Lowery acid or a Bronsted-Lowery base. No exceptions. But not all compounds that fit the Bronsted-Lowery definition fit the Arrhenius definition, such as ammonia. Now, this is the one that everybody hates. Who hates this in organic? Who hates Lewis acids and bases? Anybody going to? Yeah, you've had them. Yes. All right. Lewis acids and bases. Save this packet. All right. Lewis definitions are the broadest definitions of acids and bases. According to Lewis, this is the same Lewis that did Lewis structures. Okay?
So we don't.
You don't like him very much? That's fair. So what did he do with Lewis structures? What did we make dots of? Electrons. So Lewis likes electrons. So we're going to be, so here with Bronsted-Lowery, we're talking about protons, which is how you also refer to an H+ ion. Also known as a proton, it's the same thing. Okay. So in Lewis, we're going to talk about electrons. So acids and bases switch places. An acid. Bronsted-Lowery says it's a proton donor. So Lewis says it's an electron pair acceptor. If you think that sounds weird and confusing, you're right. A base, according to Bronsted-Lowery, is a proton acceptor, which means it is an electron pair donor. The book doesn't talk about this until much closer to the end of the chapter, but I think when you're talking about definitions of acids and bases, I needed to give you all three classifications. So here, if we draw the structure of ammonia, what kind of structure are we drawing? It's the Lewis structure. Doesn't it make sense? No, you don't like them? It's too bad. All right. So, do you see that this nitrogen has this beautiful lone pair of electrons? It wants to donate them somewhere. So this would be a Lewis base. I chose this example because we've already determined that ammonia is a base for Bronsted-Lowery. Ammonia is also a base for Lewis. It can accept another electron pair, but that doesn't really go as well. Now, you can also have a compound, I did this with fluorine. Remember, boron is happy with an incomplete octet, so it has 6. But it has a nice, beautiful empty orbital here that can accept this pair of electrons. So if it can accept a pair of electrons, this is a Lewis acid. Nowhere, according to any of our other definitions, are you going to look at that and go, yeah, that's an acid. But when you draw a Lewis, when you're looking at a Lewis definition, you need to draw the Lewis structure. So if you add those together, you get a molecule, you draw a bond right here. So you get N, H, 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 B, F, F, F. We formed a bond. Same principle applies. Any acid by either the definition is also a Lewis acid. Any base is also a Lewis base. But there are many, many Lewis acids and bases that don't fit any of the other definitions. So, all right. Any questions about definitions other than that they're weird? Do we need to see more examples? I might have to make one up. Yes?
If it fits one of those, it doesn't matter which one it is.
It depends on the definition. So if it's an Arrhenius acid, it's always an acid. Okay? Yes?
Can we think of Lewis definitions like ionic compounds?
Yes, if you're talking about charge balance.
Yes.
Yeah, you can, yeah, if that helps you. Yeah.
Awesome.
Yes?
So ammonia is not an Arrhenius base
Because it does not produce hydroxide ions.
it doesn't have oxygen.
Right. Yes, it can't produce hydroxide ions, so it cannot be an Arrhenius base. But we all know that ammonia is a base. So, according to household chemicals and a lot of the things, Bronsted-Lowery is where we'll spend most of our time talking about these acids and bases.